welcome to Lecture 6 of Linear Algebra. This lecture is on determinants. So let's start this lecture with a motivational example. Let's start by recalling that a matrix, so the definition of a non-singular matrix. So recall that a matrix A in R n by n, so a square matrix, is said to be non-singular if and only if there exists another matrix in the same space. Let's name it B. So in this case, this matrix B in R n by n, such that B times A is equal to I, to the identity matrix in that n by n space of matrices. It turns out that also A times B must equal I, but the definition is that B times A must equal I. All right? And so from this we get a theorem, which is really just an unpacking of this same definition here from our last lecture, which says that our matrix A in R n by n is non-singular if and only if A is row equivalent to I. Right? If it's row equivalent to I. All right, and so all of this then tells us that we can find a matrix which we write down, we call it the inverse of A, right? A matrix which when multiplied by A gives us the identity matrix I. So there becomes a question, right? So if we're given a matrix A, how can we determine if that matrix is singular or non-singular? So this will be our motivating question. But given a square matrix A in our n by n, can we easily tell if the matrix is singular or not? It is really non-singular, even though it's kind of the negation, right? Non-singular is what we usually want. It depends on what we're doing, but non-singular means that the inverse exists, right? So can we tell if our matrix is non-singular? So let's look at a couple of examples here, very kind of heuristic, but low-dimensional examples to try to get a feel for like an obstruction as to the answer to this question. So let's start with let's suppose that A is a 1 by 1 matrix. This is the simplest possible case, right? It's a square matrix with one entry, one row and one column. All right? So then in reality, our matrix A is really just a real number, right? So it's the number A11. There's only one position. All right? And therefore, we can treat this as though it's just a real number, okay? So the inverse, as we know, of this A11 is, let's call it B, is equal to 1 over A11. And this is only possible, right? So if and only if this entry, A11, is not equal to 0. Okay, and so this is kind of partially where the definition comes from, non-singular. So singular would mean that you would end up with 1 over 0 when you tried to find the inverse, when you tried to divide here and take the reciprocal. That would be 1 over 0. That would be a singularity, is what we call it in math. So our matrix is non-singular if we are allowed to do this, right? If you're allowed to take B equals the reciprocal, 1 over A11, and yeah, that can only happen if that number is not 0, right? So there's some criteria for our 1 by 1 matrices. Let's now take a look at a 2 by 2 matrix. So this was an exercise in the last lecture to work out a formula for the inverse of this, or work out a method of finding a row equivalent matrix for this 2 by 2, general 2 by 2 matrix here. So this is in our 2 by 2. And again, the question is, does this matrix have an inverse? Can we find a formula for the inverse of this matrix? And is there any obstruction to that, right? So would there be anything that we could just look at and see from this matrix that would make this not have an inverse, that we could just measure as a number maybe? All right, so let's write the augmented matrix then for this one. This is going to be A11, A12, A21, A22, and then we'll augment this with the identity matrix. So remember that A is going to be non-singular if it is row equivalent to I. So that means if we can perform elementary row operations to transform the left-hand side of this matrix into the identity matrix, then the right-hand side will be the inverse matrix, right? So that'll be the inverse. So as we go through, let's set some criteria here. First of all, if this matrix is going to be non-singular, then the first row, this needs to be a 1, right? When we reduce this to the identity matrix using the elementary row operations. So let's assume that, or suppose that this A11 term is non-zero. So let's suppose that A11 is not equal to 0. All right. If it is 0, then that means A21 is not 0, because otherwise, think about this. If A11 is 0 and A21 is 0, if both of these are 0, then there's going to be no way to get a 1, 0 in that first column of this matrix by using elementary row operations. It's going to be impossible. So at least one of them has to be non-zero. If this A11 is not the one that's non-zero, then the first operation you would do is to swap these two rows and then go from there. Right? So let's just assume that A11 is non-zero so that we can go through our row operations, right? And we can actually take care of this. So the first row operation that we want to do then is to divide through row 1 by A11 and make it into a 1, right? So we're going to replace a row 1. I'm going to write the row operations here. We're going to replace row 1 by 1 over A11 row 1. All right, so that's the first operation. So now our matrix is going to look like 1, and then A12 divided by A11. Over here we have 1 over A11, 0, 0, 1. The rest of this is the same, right? We haven't changed it. All right, now the next operation that we want to do is we want to get rid of this term right here. So it's basically we're just doing the Gauss-Jordan elimination here, right? We're doing Gauss-Jordan elimination with these symbolic entries. So if we want to get rid of this one, what do we have to do? We have to take row 2, and we have to add to it. It's going to now be negative A21, the negative of this, times row 1, right? And so that'll zero this out, and we'll replace row 2 with that entry. All right? So this time we're going to leave row 1 alone, and it's going to look like this still for a little while. The second row now, when we replace this is going to be zeroed out. That's by construction, right? So we have A21 minus A21. That was the whole point. We get rid of this, right? This term is going to not be zeroed out. So this is going to be A22, and then it's going to be minus this term times A21. Well, plus negative A21 times this term. So this will be minus A21 A12 over A22. All right, same thing here. This term is going to be 0, and then it's going to be minus in this case. So this will end up being negative So this will be A21 over A11, because it was 0 minus A21 over A11. And then this term is going to be row 2 minus this times row 1. So that's just going to stay a 1, right? So that'll remain a 1. All right, now the next step is going to be to turn this term into a 1. So let's zoom in on this term for a minute and see if we can add this up. This one has common denominator. So I have a typo here. You probably saw this as I wrote it. This was A22 minus this denominator should be A11. Right? Because this is the term that was subtracted. So this is the denominator from this term. All right, you probably saw that as I was writing it and you were screaming at me. Sorry I didn't hear you. Right? But we fixed it now. So now we want to combine these. So now the common denominator is going to have to be A11, right, on the bottom of all of that. And then what's here? So that's A11 times A22 minus A12 times A21. These are either order. I changed the order, but that's okay. Because they're multiplied together, right? And so that's what this term will look like. And we will see that this number that's on top here, this term on top, is going to show up throughout the rest of this. So let's give this a name to make it a little bit easier to work with. We'll call this D. This is going to be A11, A22 minus A12, A21. So this term right here we'll call D. And we can rewrite this now. I haven't done any row ops. I'm just simplifying what we've got here, right? So this is A12 over A11 here. 1 over A11, 0, 0. This is now going to be D over A11. And then negative A21 over A11, 1. Okay, so at this point, what we would like to do is make this term into a 1, right? So what do we have to do? Well, just multiply the whole row by its reciprocal, right? So we're going to replace row 2 by A11 over D times row 2. And that'll make this a 1, and then we'll be almost done, right? So at this point, we'll have, again, we haven't done anything to the first row. The second row is now going to become 0, 1. Now we're going to end up with D multiplying by D over A11. So that's just going to replace this denominator. That's going to make this minus A21 over D, right? And so this one is then just going to become A11 over D, right? Because that was a 1. So that's that. Now we have one more step to do, right? And that is to get rid of this term. So to get rid of this, we're going to do our row operation. We're going to take row 1. We're going to add to it negative A12 over A11 times row 2 and replace row 1 with this, right? So our row 2 is complete. So let's rewrite our row 2 now. So our row 2 is going to be 0, 1. Negative A21 over D, positive A11 over D. All right, and our row 1 is going to become 1, 0. We made it that way. And then we have to compute these two, though, as we go through this, right? So this one's going to be, we're multiplying by A12 over A11, right? By row 2. So this one's going to be 1 over A11 plus, right, when we add this up, plus, this is going to be then A21, A12 over A11 times D, and then we'll have to work all that out, right? This one is just going to be 0 plus, this is going to cancel out, right? So this is going to become negative A12 over A11, A11 cancel. This one's over D. And so the last thing that we have to do, we see that these all have D's in the denominator except for this one. And so the next thing that we have to do is just add this one up, right? Just very carefully add this one up. So this one's A11, 1 over A11. Let me write this more in fraction form. 1 over A11 plus A21, A12 over A11 D. This needs a D over D. All right, and so when we add this up, this is D. Remember what D is. It's A11, A22 minus A12, A21. Right, so that's all that D. All over this one. So then we're going to have a plus A21, A12, and this is all over A11 times D. Notice now a couple things are going to cancel, right? We have A21, A12. Remember, the order doesn't matter here. So these two terms are the same, and they'll cancel. And then after those are gone, then you'll see that the A11 will cancel. And so all that's left in this upper left-hand term here is A22 over D. Now, this has been, because of the symbols, probably, it's been a little bit confusing to follow, I think. Everything we've done has been totally correct. And we ended up with the right answer, it turns out. And you're probably wondering, how the heck do we know that, right? So what it turns out then is, remember that if this was A, and we did our row operations to get the identity matrix here, then this is the inverse. So this is a formula for A inverse. And so A inverse, this D is a constant, right? And that's the same in every component. So this can be factored out. It's 1 over D. And then the entries here are A22, negative A12, negative A21, A11. Okay, and from there, we can remember what this D is, right? So this will be the inverse matrix as long as this number D is not 0. And so this number is A11, A22, minus A12, A21. All right, and so this is the obstruction, the potential obstruction. So So this is what's going to determine whether or not this inverse exists, right? This number right here. So our matrix A in our 2 by 2 has an inverse matrix. In other words, it's non-singular. That was our question, right? Has an inverse matrix if and only if its entries obey this, right? The A11, A22 minus A12, A21, that this number is not 0. Okay, so now what I would like you guys to do, and we won't do this in the video, but repeat this process for a 3 by 3 matrix. It's going to get, the algebra is going to get a little bit messy, but you're going to end up with a similar criteria, okay? So repeat this process for a matrix in R 3 by 3. All right, so our matrix is going to be, I'll write out some of it and I'll tell you what the answer should be. So A11, A12, A13, A21, A22, A23, A31, A32, A33. And again, go through the row operations assuming that the first terms that you need to divide by are always non-zero. All right, and then what you'll end up with is that your similar criteria to what we've just done with the 2 by 2, you'll get a number like this, right? And so after you do this whole process for the 3 by 3, what you'll end up with is that this number, which we call D up here, right? So this number D will equal to A11 times A22. It's got 6 components. A33 minus A11, A32, A23, minus, again, I mean, it depends on how you write this, what order you get them in, but you'll have an equivalent statement here. So the next term will be something like minus A12, A21, A33, then plus A12, A31, A23, and plus A13, A21, A32, and finally minus, like I said, there's 6 different components to this. So minus A13, A31, A22, and the criteria will be that this number D, right, cannot be 0. So if your matrix, the criteria will be that for your matrix A in our 3 by 3 to be non-singular, then this number D must be non-zero. Okay, so I'll leave it as an exercise for you to work out the details of that, but it's doable. It's just like you saw on this one, it can get a little messy with the algebra. You have to be very careful to just keep straight what you're working with. So I won't make you watch me do that. But what I will say is that the reason I've named these numbers D as we've gone through is because these numbers are going to be the determinant that we define for our matrix. So, and the condition is going to be that our matrix is going to be non-singular if the determinant is not 0. Non-singular, not 0. Okay, so again, for a 1 by 1 matrix, it's just the entry itself is not 0. For a 2 by 2, the statement gets a little more complicated. We have this kind of difference, this product and difference combination here. That has to be not 0. And I've claimed that for a 3 by 3, the number is going to be this, right? It's going to be a combination of all the different entries combined in this fairly complicated looking way, okay? So we want to figure out where these numbers actually come from in a more systematic, kind of more definition driven way rather than just experimenting and seeing what the numbers become. Because when we do it this way, we don't end up with a definition for a 4 by 4 or a 5 by 5 or any larger size than a 3 by 3, right? Even if we believe this one. So what we'd like to do next then is to write out some systematic definitions for n by n matrices, and then we'll define what we call the determinant in terms of those, okay? So we'll write this as some necessary, we'll label this item here as some necessary definitions. Okay, so for all of these definitions, let's suppose that we have a generic square matrix. So let's let A be an R n by n, where n could be any number, any integer, obviously, right? So 1, 2, 3, 4, 5, 12, 100, whatever. But we'll write out, it's a square though, right? So it has the same number of columns and rows. So we'll write this out then, A11, A21 dot AN1 in the first column. And then as we move across, we have A12 to A1n. So this will be A22, A2n, AN2, all the way to ANN in the bottom corner. And so this is the entries of our square matrix. And now we're going to define some terms using this matrix. So I might draw on this matrix a little bit, but we're going to define some terms now. So there are two things here, but this one's called a minor, and the minor comes with what I call a minor matrix. Okay, so we need to define this a little bit better than I just did. This is going to be the ijth minor matrix of A, sometimes called, so everything here is either called the ijth whatever of A, or it's the whatever of the entry ij. Remember, we could write this matrix as the ij, right? Aij by its entries like this, right? So, but it's going to be called the minor matrix of A. So this is the n minus 1 by n minus 1. So it's one less row, one less column matrix determined by deleting the ith row and the jth column of A. All right, so I think for this we'll also do this by example, but the idea is if you wanted to have, say, the 2, 2, the minor for 2, 2, then what you would do is you would delete the row that it lives in, the entire row, the entire column that it lives in, and then collapse everything else into a single matrix. Okay, so that's the idea. So let's work with the following matrix as our example as we go forward here, and I'll make this very simple. So as a 3 by 3, we'll just call this 1, 2, 3, 4, 5, 6, and then 7, 8, 9. All right, so again, let's do, I drew it up here for this one, right? But this is in the second row in the third column. All right, so by the way, this is denoted by capital M, ij. So it's capital M and then the row and the column that have been deleted. So in this case, for this matrix, if this is our matrix A, then M2, 3. Right, M2, 3. Second row, third column. This is going to be a 2 by 2 matrix now, where we delete the row and the column that entry lives in, and that deletes the entry too, right? It deletes the entry as well, and it leaves us then with just a 2 by 2 matrix: 1, 2, 7, 8. Okay, so that's how this works, and you could do this for every single entry. So this is sometimes called the minor matrix for the Aij entry, right? So in this case, for the entry A2, 3, which that entry is going to be 6 in this matrix, the way that this was given, right? Now, that's called the minor matrix, and the reason it gets denoted the minor matrix is because the minor itself is the determinant of this matrix. All right, so the minor of the entry Aij, we'll write it this way this time, but the minor of Aij is the determinant. It's the determinant of M. Ij, and we'll see that the way that we define the determinant in general later on in this lecture is going to be iterative, or you could say recursive, in such a way that it's going to be the definition is going to depend on knowing the previous determinants, right? So in this case, for a 2 by 2, we know exactly how to compute this, right? We know exactly how to compute this. So in this case, the minor, we could call this one M2, 3, lowercase m. It's going to be the determinant of capital M, Ij. And by the way, let's go back to our calculation up here where we found this number, A11, A22 minus A12, A21. If we go back to the matrix A itself, that determinant is just the A11, A22 part is a product of this diagonal, and the A12, A21 is a product of this diagonal. And so we multiply those two diagonals and subtract them, right? So that's where that number D comes from. This is what we define to be our determinant up here. We didn't formally define it, right? But that's the number that we got. So, yeah. So these numbers are going to be called the determinants once we get there. But that's the idea. So, in this case, we can compute this, right? So for Mij, for this one, it's going to be 1 times 8 if we follow our rule, right? So 1 times 8 minus 2 times 7. And so this number ends up being 8 minus 14, or negative 6. And it's okay to be negative. Okay? So there's again the example for this matrix right here. So a couple more things, and then we'll do an example, another example with a matrix that actually has numbers. But the cofactor, so the ijth cofactor, of A is then given by, so this is the cofactor, right? Again, you could call this the cofactor of the Aij entry. Either way, you have to define where it is, right? You have to tell people what location this cofactor corresponds to. This one's given by capital Aij is equal to, so it's equal to this minor, but not exactly. It's equal to negative 1 to the power I plus j. So it's either going to be positive or negative depending on which location it's in. And then it's that positive or negative is multiplied by little mij, which I'll just write as determinant of capital Mij. So remember up here we had lowercase mij is equal to the determinant of capital Mij. All right. So again, for this example, our A, 2, 3, the cofactor for this 2, 3 position in this matrix that we were looking at, this one is given by this number. The negative 6 is involved, right? But it's then negative 1 to the 2 plus 3. Add the indices together. So 2 plus 3 times that negative 6. And so this is going to be negative 1. That's odd, right? So negative 1 times negative 6. So the cofactor is actually positive for this entry. It's a positive 6. Okay, so the cofactors are sometimes, depending on the location, when you add the row and the column number, the index together, if you get an even number, when you add those together, then you have a positive minor as the cofactor. Otherwise, you have a negative minor as the cofactor, but they're closely related, right? All right, before we do an example, I have one more definition. Really, I have two, I guess, because we want to define the determinant before we do an example. But so the cofactor matrix of A. Notice the cofactors are individual locations, right? And they end up being numbers. So we can arrange those cofactors into a matrix that's the same size as A. So it's also n by n. So the cofactor matrix of A is the n by n matrix whose entries are the corresponding cofactors. All right. So the entries are the cofactors, and so then we will write this as C, or if you need to, then C sub A, cofactor matrix of A, and its entries are going to be capital A11, capital A12, capital A13, etc., all the way to capital A1n, right? And so then it continues. And so each of these entries is going to be the cofactor of the corresponding position of the lowercase a, right, of the matrix A itself, whose entries are lowercase a's. So this is the cofactor matrix. Then the adjoint matrix is the transpose of this. So the adjoint matrix of A, these are all definitions that we need, okay? Adjoint matrix of A is the transpose of the cofactor matrix. Remember, the transpose switches the rows and the columns. All right, so in this case, we'll refer to our adjoint of A. We just write ADJ like this. So adjoint of A is the transpose of the cofactor matrix, which means it's going to look like, instead of the row going A11, A12, etc., that's going to become the column, right? So A11, A12 down to A1n is the first column now. The row of the cofactor becomes the column of the adjoint. And then across, we have then A21 to AN1 in the first row. And then it's very similar everywhere else, right? And so this is called the adjoint matrix of A. The adjoint matrix of A. All right, this is, like I said, it's kind of a barrage of definitions here. We're going to use all of these as we move forward, so we'll get used to them. But for now, we just have to list them, right? So now, as a separate item, I'm gonna write out our formal definition of determinant now. And the formal definition is going to use the cofactors for sure. These two matrices, the cofactor matrix and the adjoint matrix, we'll use very soon after this, but we'll see exactly how this works, okay? So here's our formal definition of determinant. I haven't even written down a definition itself of determinant other than to just, right, we've just done some examples to give us an idea of what the determinant should be. All right, so here's the formal definition. Let's let A be an n by n matrix. All right, the determinant of A. Denoted, there's two different ways to denote the determinant. We either write det of A like this for determinant of A, or you can write like absolute value sums, but be very careful because we've already seen up here with an example, the very brief example, right, that it's possible to plug into the formula of determinant and get a negative number. So it doesn't actually mean absolute value, even though the symbolism looks like it. So these are two different ways to denote the determinant. And here's the definition. So it's the scalar defined inductively, or even recursively maybe, but it's defined by the following. Inductively if you build up, recursively if you're building backwards. So they're basically, those two words mean the same thing in this context. But the determinant of A is going to be equal to just A11 if n is equal to 1. So if you're in a one-dimensional space, it's equal to 1. And then it's defined by the sum as, so I'll write it this way, sum as I goes from 1 to n of aik, a capital A-I-K, lowercase a-I-K times capital A-I-K, if n is greater than 1. And here, this is where k is equal to 1, to anything between 1 and n. Okay, so what does this mean? Well, this means to, so this formula right here, right? So let's look closer at it before we write anything else. So basically, this is telling us to take the entries in the kth row of the matrix A. So A, I, K, these represent the entries. So these are the entries in the kth row of the matrix A itself, right? The capital A-I-K are the corresponding cofactors. So the capital A-I-K are the cofactors, the corresponding cofactors of each one for each entry. Corresponding cofactors. Also, they could be considered as the kth row. So they're the entries in the kth row of C sub A, of the cofactor matrix, but that also means that then they are the entries in the kth column. So these are all different interpretations, right? So finally, or these can be considered as the entries in the kth column of the adjoint matrix. Remember, the adjoint matrix is just a transpose of the cofactor matrix. So whatever way you want to think of this, right, what you do is you look at your matrix, you pick a row, any row. According to this, it can be any row, 1 through n. So and by the way, it's actually an implicit theorem that you can choose any row here and that you'll get the same answer. We're not going to prove that, but you can choose any row, and then you expand. And so what do? You multiply the entry in that row by the cofactor that corresponds to that row. Okay, so it's entry times cofactor plus entry times cofactor, etc., all the way as you go through the entire row. All right, so let's do an example so we see exactly how this works before we list a bunch of theorems, write some more theoretical stuff here. But here's an example. So this is item 4 in the lecture. So I'm going to give you a matrix A. This one, let's do 3, 2, 4 in the first row, 1, minus 2, 3 in the second row, 2, 3, 2 in the third row. And I want you to do the following things. So I want you to find all minors and cofactors. Remember, I want the minors, not the minor matrices, but the minors themselves. So minors and cofactors. And honestly, it might help, though, the first time we do it to actually write out the minor matrices as well as the minors themselves. But then you need to convert them to the cofactors as well. Item 2, I would like to see, so find the cofactor and adjoint matrices. And again, they're closely related. So these two steps, the reason they're grouped is because the items are closely related to each other, right? So adjoint matrices. And then finally, use this information to compute the determinant. So compute the determinant of this matrix. And you can compute the determinant of any square matrix. So it doesn't, we were listing criteria at the beginning, but right now we're still talking just about the determinant. So anyway, take a moment, pause the video, try to work out these 3 to 5 items, depending on how you count them, and we'll check back in when you're done. Now that you've had a moment to work this out, let's work it out together. So I am going to arrange all of these items kind of in an array similar to what we have right here. So I'm gonna write down the minor matrices, the minors themselves, and the cofactors kind of spread out in this array. All right. So I'm gonna have row 1, and then up here I'll have the columns. All right. So column 1, 2, 3, and then let's just arrange these. And we'll see how much room we need, but I'll space them out a little bit. So 1, 2, and 3. So first of all, the minor matrix M11, right? This is the matrix obtained by doing what? By taking the entry in the first row in the first column and then deleting the first row in the first column. So the first minor matrix is minus 2, 3, 3, 2. And I'm just going to go through and write down all the minor matrices first. So the next minor matrix, M12, this is obtained by deleting the first row and the second column. So this one will be 1, 2, 3, 2, right? First row, second column, you're left with these 4. Finally, M13, this is obtained by deleting the first row, third column. So you get 1, minus 2, 2, and then 3. All right. So then, let's see. The next one, this will be M21. Second row, first column. This is going to leave us with second row, first column, 2, 4, 3, 2. Right? M22, this is going to leave us with just the 4 corners, right? So 3, 4, 2, 2. And then M23. For this one, we delete second row, third column. We're left with 3, 2, 2, 3. So again, I'm just writing down all the minors first. So then M31, that's going to be this upper corner, right? So it's going to leave us with 2, 4, negative 2, 3. M32 deletes the third row in the second column. So we're left with 3, 4, 1, 3. And then M33, that deletes third row, third column, leaves us with 3, 2, 1, minus 2. All right, now we compute the determinants of each of these, right? So little m11, this is the determinant of the 2 by 2, and we define this to just be this crisscross product, right? So minus 4, so I'll write it out. It's negative 4, minus 9, and so this is negative 13. All right, and then we go to the next one. So lowercase m12, this is going to be 1 times 2, so 2 minus 6. So this one's negative 4. And then we just continue, right? So lowercase m13. These are the minors. So actually, these are what was asked for, right? The minors. So this is then 3 minus negative 4 That's positive 7. Here we have lowercase m21 is going to be equal to 4 minus 12. So this is minus 8. Lowercase m22 is 6 minus 8. So that's negative 2. Lowercase m23, this one's going to be equal to 9 minus 4. So that's 5. It's a little probably boring listening to this, right? But you guys already worked it out. So this one's going to be 6 plus 8. So this one's 14. Lowercase m32 is 9 minus 4. So that's also 5. And lowercase m33 is negative 6 minus 2. So that's negative 8. Okay, so that's just working through those. Now we need to find the cofactors, right? So the cofactors are obtained by taking the minors and multiplying them by minus 1 to the power, where you add together the coefficients, or the indices, right? So the indices are going to always rotate. So 1, 1 is even, 1 plus 2 is odd, 1 plus 3 is even, 2 plus 1 is odd, even, odd, even, odd, even. I got off track there, right? So this goes even here, odd, even, odd, yeah, even. Okay, I guess I had it right. But the whole idea is that when it's even, you're going to just leave it alone, right? So capital A11 for the cofactor is negative 13. Nothing to do with it. It's negative 1 squared times 13. Capital A12, this one is going to be negative 1 times negative 4. So this is going to be positive 4. All right, so capital A13, these are even, you leave it alone. Now, capital A21, this is going to be negative 1 times negative 8, so that becomes positive 8. Capital A22, we leave it alone, negative 2. Capital A23 is negative 1 times 5, so that's negative 5. Capital A31, leave it alone, that's 14, it's even, right? Capital A32, this is odd, so negative 1 times 5, it's negative 5. And then capital A33, leave it alone. All right, so after all this, we have found, finally, all of our cofactors, right? So our cofactors for each entry we have found. And now we need to collect them into a matrix. So our cofactor matrix of A is just going to be arranged in the exact same way that we've got it here, right? So it's the matrix whose cofactors line up exactly with the arguments that they came from, right? So this one's going to be negative 13, 4, 7 across the first row. Then 8, negative 2, negative 5, second row. 14, negative 5, negative 8 for the third row. So that's the cofactor matrix. The adjoint matrix is the transpose of this. So the adjoint matrix along the first row has negative 13, 8, and 14. Along the second row, it has the second column up here, right? So 4, minus 2, minus 5. And then the third row is 7, minus 5, minus 8. So that's the adjoint matrix. Okay, now let's remember what A is. Let's copy A and write A down here as well. So here's A. Let's write it like this, actually. Well, we can match this up however we want. But now for A, what we need to do is to compute the determinant. What we need to do is choose a row or a column of A and expand on it. So, I mean, we haven't talked about the columns yet, but to choose any row. So by our definition, we choose any row. Let's just choose the first row. So the first row of A, we need to multiply the entries of this by the first row of the cofactor matrix, right? So entry by entry, we multiply these together and we add them up. Notice that that is the same as multiplying by the first column of the adjoint matrix. All right, it's the same as multiplying by the first column of the adjoint matrix. But we'll get to that a little bit later. So for this one, what we need to do then to determine our determinant, remember two different notations here, is just go entry by entry, right? So I'll write this out in terms, we have A11 times capital A11 plus lowercase a12 capital A12, lowercase a13 times capital A13. So I've chosen to use row 1. That's where all these numbers come from. And this is just going to be 3 times negative 13 plus, you just write them out now, 2 times 4 plus 4 times 7, right? So this will be negative 39 plus 8 plus 28. And so this is 36. This is negative 39, so this ends up being negative 3. Right? Let's just make sure I work that out properly, but that's the determinant of this matrix. And notice that's not 0, right? As long as it's not 0, then this matrix is non-singular. But there's our determinant, and that was really, that's the ultimate goal of this example, was to find the determinant of this matrix A. All right, so that's the determinant of A. Now, we did a lot more work than we had to if we were really only asked to find the determinant. We were asked to find all these parts, right? But if it just skipped to item 3 here and said compute the determinant, then actually all we have to do is pick our favorite row or column to start with, and then only compute the cofactors that are necessary in this computation, right? So that's something to keep in mind if you're just asked to find the determinant and not asked to compute all the other stuff. If you are asked to compute everything, then you got to do everything we did, right? Actually compute all the parts. All right, so you can line these up in some kind of a table like we did, or just as long as you're organized, doesn't really matter how you organize it, right? As long as it works and you get the right answer in the end. All right, now the next thing I'd like to do is just list some theorems without proof. So I'm going to state some theorems without proof about determinants, and we'll just believe some of these will be exercises to prove, actually. For the sake of this lecture, let's say that all of them are exercises for you to prove them. They're all provable in some sense, but for the sake of time, and this lecture is going to be a long one anyway, let's just state these without proof right now. So some theorems without proof. So these are theorems about determinants. All right, I'll just list these. I'll number them out. Number 1. I've already said this a couple times, but the cofactor expansion can be done on any row or column. So the cofactor expansion, that's the definition that we used, and we just did right here, right? Cofactor expansion. Multiply the elements by their cofactors and then add them all up. That's called the cofactor expansion. So the cofactor expansion can be done on any row or column. And of course you just have to pick your favorite, right? So the determinant then of A is, on one hand, it's the sum. I goes from 1 to n of lowercase, I always write the capital one first, lowercase aik times capital AIK, or it's also equal to the sum j goes from 1 to n of lowercase a kj capital A kj. So this is rows and this is columns. Okay, but expanding on a row, the kth row, this is the kth row, this is the kth column. So in this case, the k you choose, and then it would stay fixed, right, for that computation. All right, so there's one theorem that can be easily verified. Next theorem, number 2 here. This one is very simple. So the determinant of A transpose, if you believe the previous statement, then the determinant of A transpose must be the same as the determinant of A, right? Because all that does is swap the rows and the columns. And if you're allowed to use rows or columns anyway, then swapping them won't change your answer, right? If you're computing the determinant. So there's a theorem. Furthermore here, if A is a triangular matrix, so if A, obviously they're all square, right? If we're talking about determinants, then we're talking square. But if this is triangular, so by triangular I mean either upper triangular, lower triangular, or diagonal. So any one of those is fine. But if it's triangular in any way, then the determinant of A is equal to the product of the diagonal entries. But this is only true when the matrix is triangular. So it's equal to the product of A's, we'll say, diagonal entries. Okay, so for a triangular matrix, you think of our upper triangular matrices from the LU factorizations, right? Those matrices, their determinant is the product of the diagonal elements. All right, so there's another. We'll see it as we move forward, especially in exercises as you study. The LU factorization can be helpful in computing the determinant of a matrix as well as solving systems like we used it for in the last lecture. All right, a couple more here. Here's some criteria for when the determinant might be 0. So let's let A, again, be a square matrix. Then the following are just true. These are facts. If A has any row or column that's all zeros, then its determinant is 0. And we already talked about this when we were using our motivational example back there, right, at the very beginning. So if A has any row or column with all zeros in the entries, right, then the determinant is 0. All right. Similarly, if A has two identical rows or columns, then the determinant is also 0. So this is because we can do elementary row operations to zero out one of those rows, right? If we believe the first one, I mean, actually, we should definitely believe the first one, because if it has a row of all zeros, then you expand on that row, and all of the lowercase a's will be zeros, right? So 0 times whatever is always going to equal 0. Add them up, you get 0. So if we believe this first one, then the second one's also going to be true, right? So if A has two identical rows or columns, or really if they're combinations of each other, but two identical rows or columns. So in this case, I mean two rows that are the same or two columns that are the same. Then the determinant is also 0. Okay, by a simple row operation to get rid of one of them, and then you're back to case A here. All right, theorem number 5. This one says, and this one requires a little more work than the other ones, but this one, again, I'm going to leave as an exercise. So the other ones are kind of just straightforward from the definition. But for this one's very important, though. So if A is an n by n matrix, then the following is true. So the sum of, as k goes from 1 to n, of aik times capital A jk. So the idea here is that we're multiplying one row of the matrix by potentially a different row of the cofactor matrix. All right, so one row of the entries of the given matrix times a potentially different row of the entries of the cofactor matrix. This one's going to be equal to, obviously it's the determinant of A if I equals j. That's the definition, right, of our determinant. If I and j are the same, that's the cofactor expansion. But it turns out that it's equal to 0 if I is not equal to j. All right, and so this second line here, that's definitely, of all these are all recommended that you try to work out the proofs of these, but that second line there, that if you multiply, say, the first row of the matrix times the entries of the cofactors of the third row, then those will always add up to 0. All right, you can check that. You can work that out. But that is true. So we're going to take it without proof. We're going to believe it without proof right now. And then finally, the statement that motivated everything from the beginning of this lecture is the following, right? A matrix A that is a square matrix. So a square matrix A in our n by n is non-singular if and only if the determinant of A is not 0. So if it's 0, the matrix is singular. Otherwise, the matrix is said to be non-singular. All right. That obviously was the motivating fact that we were looking for, right, when we defined the determinant to begin with. Our motivating question was, how can we tell if a matrix is singular or not without actually having to find the inverse, right? So there you go. We can compute its determinant, and then that number will tell us, is this matrix singular or is it non-singular? All right, so there's a bunch of theorems, 6 theorems without proof, stated without proof. Again, they are all true, and we're going to use at least one of them in the next little segment here. So this is item 6 of the lecture, as opposed to theorem number 6. What we'd like to do next is kind of investigate that adjoint matrix a little bit more. So let's let A, once again, be an n by n matrix. And then similarly, let CA be the cofactor matrix, and the adjoint of A, right, which is the transpose of the cofactor matrix. So these are going to be the cofactor and adjoint matrices. Of A, respectively, right? All right, what I'd like to do now is consider the product of A times the adjoint matrix. So now let's consider this. So let's consider A times the adjoint matrix. So A times, I'm drawing a dot, but that's not a dot product. That's, let me get rid of it. It's A times the adjoint matrix. All right. So let's write out the terms of these. This is going to be A11, A12, all the way up through A1n, right? A21, A22 through A2n, AN1, AN2 to ANN. And then the cofactor matrix, remember, is the transpose, sorry, the adjoint matrix is the transpose of the cofactor. So this is going to be A11, A12, A1n is the first row, column, first column, as opposed to the row. And then A21, etc., right? And this goes over to AN1, AN2, ANN. And we want to multiply these together. So I'm going to just write out a couple of them, and then we'll do like a dot, dot, dot. We'll be able to see how this works, I think. But let me highlight these. So the first one we want to do is the 1-1 position of the product is going to be the first row of A times the first row of, the first column of the adjoint matrix. And when we write this out, look what happens. We get A11 times capital A11 plus lower A12 times capital A12, etc., all the way up through lower A1n, capital A1n. All right, so that's all in the A11 position. So that's in the 1-1 position of the product, I should say. All right, as we move to the next one, so let me get the highlighter back. Let's say we move down to the next row here, right? So row 2 times column 1 in the A12 position. Right, what's going to happen there? Well, now this is going to be A21 times A11 plus A22 times A12, etc., all the way up through A2n, capital A1n. All right, so and then it's going to continue, right? We go through row, row, row. All these are going to be multiplied by the first column, and then we'll go over to the next one, etc., etc. So I'll just draw some dots here. But then let's go back and, again, if we believe this theorem, I said this theorem was going to be very important, right? So if we believe this theorem, the blue highlighted version, which this is the one in the blue, is going to be the first row times the first column, right? That one is going to satisfy this, right? That it's going to be the same row, so that it's going to be the row of the matrix times the corresponding column of the adjoint matrix, right? So that's going to be the determinant. So this term right here in the first entry of this product is going to be the determinant. All the other ones in the first column, these are different rows times the first column, right? So those are all going to fall under this second criteria, where the row does not equal the column. And so in this case, they all equal this, right? And so all of these are going to be zeros. So that'll be 0, and then we'll have zeros through here. So you guys can take a few minutes to work this out in more detail if that wasn't enough for you. But when you multiply all this out, what you're going to end up with is the following. You're going to end up with the determinant of A along the diagonal. So that whatever the number is that's the determinant of A will be along the diagonal. And there's going to be zeros everywhere else in this matrix. All right, and so what we end up with at the very end is that A times its adjoint matrix, A times its adjoint matrix is equal to, we can factor out this determinant. So we can factor out the determinant of A, and then what's left will just be the identity matrix. So this is almost exactly what you want when you're trying to find the inverse of a matrix, right? But we don't want this determinant, we just want I. So again, if the determinant is non-zero, so this again leads back to our original question, right, about singularity and inverse. But if the determinant of A is not 0, then what we've actually shown here is that A times this matrix, which is built by the determinant of A times the adjoint matrix, this is equal to I. And if you have a matrix times another matrix equals identity, what must this matrix be? This matrix must be the inverse, right? This must be A inverse. Okay? And so we can call this another theorem, right? We've obtained a theorem here. So let's let A in Rn by n be non-singular. This means that it has an inverse, and for it to have an inverse, it means that the determinant must be non-zero, right? So what we then have learned is that the inverse of A is equal to scalar, 1 over the determinant as a scalar, times the matrix adjoint of A. All right, so this is a scalar times the adjoint matrix, and you could obviously combine that all into one matrix, but there's a formula for the inverse of A in terms of the adjoint matrix. All right, and so this can save us, depending on the matrix itself, how big it is, this can save us a lot of work where we won't have to do all the row operations, and we saw how much of a mess that was even for a 2 by 2 above. But you can compare this actually with our work for the 2 by 2, the determinant and the adjoint. It'll be an exercise in your homework to show that actually this formula is exactly the same one that we got way back at the beginning of our studies for our 2 by 2. So back here, we said, right, that this number is the determinant of our 2 by 2 matrix, 1 over D, right? There's our determinant. And then the rest of this, it turns out, this is the adjoint. So it takes you just have to work out a couple of items, but 1 over the determinant times the adjoint, that equals the inverse. Okay? So that, especially for 2 by 2, that's a formula that you can just remember. Okay? But we've just proven it with this theorem. We've worked it out. After we had to define all the pieces that went into this, right? But after defining all those pieces, we got this very nice result. Okay, there's one more thing that we want to do in this lecture. I'm going to, again, it's another kind of theoretical thing, but I'm going to write out something called Cramer's rule. This is another theorem, but Cramer's rule, and then we'll use it to actually solve a system of equations, and then this very long lecture will come to an end. But this item is called Cramer's rule. And this is a way of solving systems of equations using matrices and their determinants. So here's the scenario, okay? So let's let A be an n by n matrix, and suppose that it's non-singular. So we'll start off with a non-singular matrix. And let's let B be any vector in Rn. So it's a square system with a non-singular matrix, right? One of our theorems from the previous lecture is that this system, A times x equals B, has a unique solution. So if your matrix is non-singular, then you end up with a unique solution, right? There's only one solution. We'll call, this in this scenario here, this is x, right? But let's call it x. We'll actually call it x. All right, and then here's how we're going to find it. So this is the deal then. So now let's let A sub I represent the matrix obtained by replacing the ith row, let's do it by column. Ith column of A with the vector B from the right-hand side. All right, so A sub I is that matrix, the new matrix with one column replaced by the column B, all right, the column vector B, which is the right-hand side of our system. And then here's what Cramer rule says. The solution of the system AX equals B, right, is given by X equal to X1 to Xn. All right, and the reason I write it like this is because I'm going to write now entry by entry. X sub I, that's the ith entry of the solution, is equal to the determinant of the ith matrix that we built from here, divided by the determinant of the coefficient matrix A of the system. All right, so now I'm using the vertical bars to represent the determinants here. All right, let's prove this one. This one can be done by a proof. Well, we know that, I won't write a whole bunch of words here, but we know that the solution vector, because A is non-singular, it's just going to be equal to A inverse times B. Just multiply A inverse on both sides of your equation, and that'll isolate the X for you, right? But based on our previous work, we now also have a formula, right? A formula for our inverse. So this is going to be 1 over the determinant of A. All right, let me actually write it in the same notation that I used here. So in that notation, it's going to be 1 over determinant of A times the adjoint matrix of A times B. All right, and so then in the ith entry, what is it going to be? The ith entry of this is going to be the ith row of A times B. So X times, X is this. This is our answer, just by, we already know it's the inverse of A times B. Now we have a different formula for our inverse. So when we work this out, the ith entry of this solution vector over here is going to be 1 over the determinant, hangs around, right? And then it's going to be the entries in the ith row times B. So what's it going to be? It's going to be B1 times A in the ith row. It's going to be I1 plus B2 AI2 plus all the way through BN AIN. All right, and if you think about the matrix that you get by replacing a row, or a column I should say, with the vector B, what you'll find, right, is that actually the cofactors are the same. The cofactors for all the elements that correspond to the column of B are exactly the same, right? And so this term right here ends up being the determinant of that matrix AI. So this ends up being the determinant of that matrix where you replace the ith column by B. And it's really that simple. It's just a matter of unpacking the definition. The definition, I guess it's not a definition, but this formula for the inverse matrix that we got just above, right? But from this theorem. 1 over the determinant of A times the adjoint matrix of A. So that's it. So this is Cramer's rule. And now let's use it. So this is the real key, right? So what we want to do then to solve our system is there's going to be, depending on the size of the system, we want to find all our matrices, compute the determinants, and then just divide those numbers, and then we'll have our solution. So let's do one final example to close out this lecture. So I would like you guys to use Cramer's rule to solve this system. So here's a system of equations. x1 plus 3x2 plus x3 equals 1. 2x1 plus x2 plus x3 equals 5. Negative 2x1 plus 2x2 minus x3 equals negative 8. All right, so try to at least get this started as far as you can on your own. But what you're going to want to do is rewrite this system as a matrix equation. A times x equals b. So you'll identify the coefficient matrix A. You'll identify the vector B. You can take the determinant of A and then systematically replace the columns one at a time with the vector B. Take the new determinants, right? And see how it goes. So I'll give you guys a few minutes to work on that, or you're going to give yourself a few minutes, right? Take a pause the video, work this out, and when you come back, we'll finish this one off together. All right, let's work on this together now. So the first thing that we should do is write out the coefficient matrix. So it's going to be 1, 3, 1 in the first row. Everything's lined up properly by the variables, right? You always have to check that just to make sure, right? But the coefficient, the second row of the coefficient matrix will be 2, 1, 1, and the third row is going to be -2, 2, -1. The unknown, obviously, is vector x. Let's call this, just for our sake, x, y, z. Then we can just write those out in these terms. You don't have to do this, right? But the vector b is going to be, well, I shouldn't call it x, y, z. The unknowns are given to us, right? It's x1, x2, and x3. So let's leave them the same as they were given. If you want to call them x, y, z, it doesn't hurt, right? But technically, we should give back the answer in the form that it was given, the question was given to us, right? So then finally, the vector b is going to be 1, 5, and then -8. And now to apply Cramer's rule, we just have to take 4 determinants, right? So let's start with the determinant of a. Now, I'm going to show you guys a trick here. It's kind of a trick. You might have learned this in a calculus class, Calc 2 or Calc 3. But one thing that you can do is write out your matrix. So if you want to take the determinant of a 3 by 3 matrix, you write out, this works for any size, by the way. But you write out the matrix, you then add however many rows you need to make it so you have, we're gonna repeat actually these 2 rows, these 2 columns, I should say. So we're gonna repeat, let me put these in a different color. So outside of the matrix, I'm gonna repeat the columns 1, 2, -2, and then 3, 1, 2. And the reason I put an extra 2 columns here is because now the method is to multiply together the diagonal entries going this way. All right, and so those are all going to get added up. So on the main diagonal, and then it's 2 parallels. So that's why I needed 2 extra columns, right? And then I'm going to subtract the products of these. All right, those are going to get subtracted. And so now I can, without a whole lot of writing, I can very quickly compute this determinant. So the determinant is going to be 1 times -1, right? So it's going to be -1 plus the next one. So 3 times -2, so that's going to be -6 plus 4, right? And then I'm going to subtract the rest of them. So I'm going to do a big minus and then put all these as positive. But this is going to be -6 plus, this is going to be 2, plus this product is going to be -2. And I've got this minus sign in front of all of it, right? So that's the way I did it. And so now I'm just going to group these. So group these up. So really, the way I've done this, I should have probably color-coded, right? So it's going to be the blue ones get added, and then the green ones get subtracted. All right, so there's the color coding. So now what's it going to be? Well, this is going to be -3 minus, this is going to end up being -6, right? So -3 minus -6, that's just 3. Okay, so now what do we have to do? Now we have to write out our next couple matrices. So A1, the matrix A1, we can do this in to save some writing. We can do a couple steps at once here. But the matrix A1 with a determinant, that's going to be the one. Let's, I like to color code stuff. It just really helps me keep everything straight. Let's make this vector like a baby blue color. And actually, I'm just going to copy this. So if you're working on a computer, you can do this too. And then that's going to become the first row of my matrix. Sorry, the first column of my matrix now, right? And the next 2 columns stay the same. So 3, 1, 2, 1, 1, -1. This is what I want to take the determinant of. So I can repeat the same process we just did up here, right? Which is repeat. Now I have to make sure I'm repeating the first column, which is now the new one, right? And then the second column, and then I can go through with my diagonals again, right? Just be careful as you do it. But those get added. These get subtracted. And so, very carefully, what do we have? This one's going to be -1 plus, this is going to be -24 plus, this one's going to be 10. And then we're going to take away the green ones, right? So -15 plus 2 minus 8. All right, and then just carefully work it out. So this is going to be -25 plus 10. So that's -15 minus, over here we have -23 plus 2, so -21. And so this is all going to end up being 21 minus 15, so this is 6. So the determinant of A1 is 6. All right, and then we just continue this. So determinant of A2 equals, first column is 1, 2, -2. Second column is B, right? Third column is 1, 1, -1, and then same process. So now we just repeat our process where we go through here and very carefully multiply these diagonals, add up the main diagonals, subtract off the off-diagonal entries. So, all right, this one's going to be what? -5. This one's going to be -2, and then -16. And then we're going to take away -2 plus -8 plus -10. And then very carefully work it out, right? So -21, so -23, minus, now over here we had -20, right? And so altogether this is -3. All right, and then we have one more. So a little bit tedious, but with this crisscross method, which again, this works with any size matrix. If you go to 4 by 4, you just have 4 of these diagonals you have to compute. 12 by 12, you have 12 of these diagonals, right? So 24 altogether. It's always doubled. So whatever your dimension is, so this is 3-dimensional, right? So 3 in the positive direction, 3 in the negative direction that way. So here's our matrix again. 1, 2, -2. 3, 1, 2. Now we replace the third column by B, and then we rewrite these. These columns the only thing you need to really make sure of is that you copy correctly, right? And then again we have blue, 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 green, green, green. All right, so let's see. This one's -8 plus. This one's -30. And this one's +4. Right? And then this one's going to be what? -48. And this one's going to be +10. And then -2. So -38 plus 4, that's -34 in this one. And then minus, this is going to be -50 plus 10, so -40. And when we add this together, we get 6, right? So there we go. All right, now we just have to put everything together to get our solutions, right? So we've got all these determinants worked out, and we just have to put this together by Cramer's rule. So x1 is going to be determinant of A1 over determinant of A. Determinant of A1 is 6. Determinant of A is this up here. It's 3. Right? So this is 6 over 3. So this is 2. X2 is equal determinant of A2 over determinant of A, which is -3 over 3. So that's -1. And then X3 is determinant of A3 over determinant A. This one is also 6 over 3. So this one's also 2. And so the solution of our system is that X is equal to 2, -1, 2 by Cramer's rule. All right, so yeah, so there's an application of Cramer's rule with a little bit of a computational shortcut there for you if you've never seen that, to help you compute the determinant quickly. But this lecture is long enough at this point. Hopefully these examples have helped you a little bit. Lots of theoretical stuff here. Make sure you're going through the text and working through this on your own. And I'll see you guys in the next lecture.